Hey! It is. It's quite nice. It's a little skewed, not perfectly symmetric, but it's quite nice. It really is.
Right, well, if I do my InClass Theorem.
Look at that. Are you using the presets, I'm thinking? Using the presets, you can knock the X scale down to 1. Make it look prettier. You never hear that adjective enough in this class. This looks pretty. I love that. It makes me happy.
He's not a very good teacher.
I know I'm right here, though. I know we're all over that stuff. Okay, so friends, I want to regroup. Make sure we're on the same page. So here's typical dice. This is the distribution we played with last week and the week before that. Fairly straightforward, up, then back down, straight line. Here's each of the ones you guys had to mess with. Here's the blue distribution. Look roughly what you guys came up with the blue dice, you guys. We may have been off by 1 or 2, but I'm guessing it's pretty close to what you guys got.
Yeah.
We got an average of 8.2-ish, 8.16666, and then we got a standard deviation 2.65-ish, somewhere in there. What's interesting about this one is you've got the skew, it's skewed left, leaning right, you got like 3 modes. I just couldn't resist but make these dice just because of that, because it's ridiculous. Yeah. It's ridiculous, yeah? The average is more to this side than normal dice, because you've got more frequency on this side of 7 than that side, which I think makes sense. But definitely an interesting graph. But you wouldn't call it bell-shaped, and you wouldn't call it binomial. So that makes it a fun distribution because it doesn't fit one of the models. That's the whole point of talking about it today. Here's yellow. Here's the yellow dice. Yep. These look almost exponential. This was that goofy 13 that we had to figure out with the yellow dice. We were the 13 threes. So you got a very much a unimodal distribution, but it's not bell-shaped at all. It's got a long, long tail. You have these couple of an occurrence of 11 out here in the wings, which is kind of throwing things off. I get an average of 4.5. Yep. Good with you guys? Good. Standard deviation 2.22-ish. Good. There's the yellow dice. Here's the greens. The greens were fun. The greens, I was shooting for the greens. I was trying to get a curve that went like this. In other words, a U-shape. Maybe not that sound, which was very fun. Why couldn't I get a U-shaped curve?
So there's a bunch of 6s and 1s.
Because if I have a bunch of 12s and a bunch of 2s, that means I got a bunch of 6s and 1s, which necessitates the fact that I also have to have a bunch of 7s. So I tried for a while, then I'm like, it's not going to happen. This is close-ish. So it's definitely symmetric. Definitely symmetric, but it's got so many gaps in it that you can call it bell-shaped-ish. You could stretch of a bell. But at the same time, it's definitely different enough. Definitely symmetric, which is one of the only, I think it's the only of the 5 that is symmetric. It's got its average perfectly at 7, just like the other distribution. But notice it's got a wider sigma than the fair dice. The sigma for the fair dice was 2.4. This is 2.9. Why is the sigma wider on this one than this one? So there's that one. There's the fair dice. Why is sigma wider here than here, if the average is the same?
I would think it's because you got 2 2s and 2 12s on
We've got more at the outsides than we do with the fair dice. More at the outsides. When I say outside, I mean further from average. The definition of standard deviation is average distance from average. So if on average you've got more further away from average, that has to go bigger, because you're traveling further to get to the average, on average. Even though you've got the most at 7, just like you did on the other one, you've got more clumpage happening at the outsides. Clumpage, not a real word, but we're going to make it up here. Cool! Orange! This was just ridiculous. It was a fun, ridiculous distribution. Stupid bimodal, gaps everywhere. You've got this clump here. You got this clump here. Beautiful distribution. And stupid all at the same time. I got an average of 7. You guys? Is that good? Yeah, average of 7. I mean, you look at this, it's like, how can the average be 7? Because it is. Because we've defined the average to be the sum of the data points divided by 36, and the average is 7. I'm not saying you should use 7 in this case, but if you needed to know what the average was, for example, and Dana, you asked a great question about a week ago, if something has a shape like this, why would you even talk about the average? Because that's what the average does. On average, that's what happens. Yes, sure, we've got 2 modes that are nowhere near average, but the average still comes out being 7. So if you have something that happens over millions and millions and millions of trials, that's what's going to average. So granted, it could be misleading in a small sample, but when that population becomes a population, that's when we actually care about it. Thank you. Great question last week. Very tight standard deviation, 2.15. Because, again, clumped. There's no wicked extremes at 11 and 12 or 2 and 3. They're all between 5 and 10, or 4 and 10. And last but not least, the only one even remotely resembling a bell curve was the red dice, right? Now, the fact that it's compressed, instead of covering the entire 2 through 12, it covered 6 through 12. And this one, the 9s and 10s were the pain to count here. These 9s and 10s were a total pain. 9 of them and 8 of them. So there you go. A high average, the highest average of the bunch, 9.2-ish. And look at this. Look at the sigma. Extraordinarily small. Why?
Because they're clumped.
Because they're clumped in. So what you're seeing is the wider sigmas, the wider sigmas are on the more extreme data, more extremely spread data, and the tighter sigmas are on the good. Fantastic. Katie?
So why did you use the population standard deviation?
Because, very good question. Who wants to answer it? Katie asked an excellent question. Why am I calling this sigma and not S? Madeline, go.
Because that is the population.
That is everything that can happen on this pair of dice. This is one of those strangely fictitious examples where you're actually holding the whole population in your hand. More on that in about 30 seconds, but that's why, Katie, because that is sigma. Anytime you're dealing with a probability distribution, which I know we're not dealing with yet, I haven't changed it to a probability distribution yet, it could be though, you have the entire population in your hands, which means there's no unknown of a sample. This goes back also to Danny's question about, wait a minute, time out. If this is that skewed, should you be talking about the average? Well, it's the population that's that skewed, so you can call it mu, and you can say it with confidence because it's an entire population, not just a sample. Great question, great question. Anything else? Fair enough? Now here's the fiction. Here's the fiction, and it ties into what Katie just said. The fiction is that you're not going to get that in reality. You're not going to get the entire population delivered into your lap. You're going to get a sample of some population. And you have to derive from that sample some information. That's the kicker. This goes back into Danny's question about calling mu. We're going to leave mu alone for a while. We're going to call it X bar again, because we're going to go back to sampling. Real quick, and the reason I'm doing this, I like having this last lesson before we go into 244, because those of you joining us for the journey in 244, that's all we do is estimate parameters. So we don't know what mu is, but we want to know what mu is within a certain bounds of confidence or something. So the idea is we're not going to know. We do know what mu is for these dice, which is good, because what I want to see next is I want to see if we can figure out what these are experimentally. So we know what they are. Keep them handy. What we're going to do next is we're going to do a little in-class quiz using your dice. Because sometimes, my goodness, we got some statistics allergies going on today. So we want to know mu, and maybe sigma too. I feel like Dr. Seuss now. We want to know these things, but we never can know these things. Because the populations are usually too big. So what you're going to end up having to do is draw samples from a population. Look at your sample, take measurements on the sample, and see how that relates to your population. That's why I had you do the population supposition first. Get the values that you know you're shooting for. Then when you do your sample, you can compare them to that value and see how close you got. Now you can't do this in the real world most of the time, yeah? You can do it in Vegas. We just did it in Math 105 with craps. We just figured out, theoretically and empirically, the chance of winning craps on a pass line bet. Okay? But the trick is that their sample was a little bit skewed. I didn't get into standard deviation with them, because they had enough after averages. But we understand standard deviation. So the idea is, can we get a value for mu that's close enough to the true value that if we put some wings on our estimate, we trap the true value? That's what 244 is all about. That's what we're going to start a little bit in right now. But it starts with your dice. It starts with your dice. So what I'm going to do is I'm going to give each group an in-class quiz that will spend, it'll probably take us most of the rest of the class to go through. I'm thinking, take your time with it, take your time with it. So let's grab this. It's a 2-pager, and it's what's that called? Landscape?
Hot dog.
Hot dog style? I like that. Hot dog, what do they call that?
That's
When you fold it, hot dog or hamburger
Oh, that's so cute.
When did that?
That's adorable. I've never heard that before. Hot dog. Microsoft would become infinitely more popular if they changed it to hot dog and hamburger. Maybe not with the vegetarians, but oh my god. All right, so one per quiz. It's adorable. Hot dog and a hamburger. That makes me so happy. Then you make it in triangles, we do pizza. Oh, the possibilities are endless. I think I can turn this off now.